Hello and welcome back to the Hutchins School Chemistry Lab. I am Dr. James and today we'll be discussing the reactions of alcohols. Let's get to it. Alcohols come in three types, primary, secondary and tertiary, as we've already discussed. And in today's lesson we'll be looking at the following dot points, which again I won't read to you because you can pause and read these for yourself. But suffice to say, this is what we'll be talking about. Let's move on. When we oxidize alcohols by using an oxidizing agent, the products will depend on the type of alcohol that we start with. Primary, secondary and tertiary alcohols all produce different products under oxidizing conditions. And those products depend largely on the starting material, but also depend on the stoichiometry and the strength of the oxidizer that's used. Here you can see I've got a primary alcohol drawn. I've labeled the alcohol group in red, and I've labeled the alpha hydrogen in blue. Let's zoom in on that a little. Here we see just the key detail of the alpha carbon, the alpha hydrogen, and our alcohol group. So that we can fully understand the bonding situation for this alcohol, we're going to draw in all of the electrons that are present in these bonds. You can see that I've represented the electrons of the alcoholic oxygen as X's, and I've used dots to represent the electron of the hydrogen. The electrons of the carbon, I've only shown two here because there are two more in these other bonds that I haven't drawn any details on. And finally, I've represented the electrons of the alpha hydrogen as an X. The reason that we know these numbers is based on the periodic table. We know that in group 16, oxygen has 6 valence electrons. Hydrogen in group 1 has 1 valence electron, carbon has 4 valence electrons, and I've only shown 2 of them, and so we get this situation. We also know that each one of these atoms likes to share electrons to achieve a full valence shell. I want to show you what happens when we undertake an oxidation reaction, but I can't show you the mechanistic detail, which is the really accurate detail of what actually happens. We don't need that in our course, and it's a little bit too detailed and includes a few things that will be a little bit confusing. So rather than that, what I'm going to do is introduce an oxidizer, and that will be an oxygen atom in square brackets. It's going to come in and it's going to attack at the hydrogen of the alcohol group. When it does that, it's going to take not only that hydrogen away, it's also going to take both electrons from that bond between oxygen and hydrogen. Since this is an oxidizer, the thing that is getting oxidized, which is our alcohol, is going to lose electrons, and that's what we see happen. Because it's taken the hydrogen and the electrons, we potentially have formed a hydroxide group, or we can access a hydroxide group from some other chemical species. The details of that doesn't matter. What happens is in this next stage we get a hydroxide attacking, and this time it takes the hydrogen only and it leaves the electron. Now we're in this state. This is quite unstable. You can see oxygen has 6 electrons around it, and this carbon here has 8 electrons around it. But if we rearrange a little bit, we could have carbon and oxygen both with 8. We can do that by moving the electrons from this single bond, formerly to the alpha hydrogen, all the way up into forming a double bond between carbon and oxygen. Remembering, of course, that each bond represents 2 electrons being shared between 2 atoms. This CO group is the basis of a couple of our products of oxidation of alcohols. The first of them, if this was a carbon and this a hydrogen, would be that we formed an aldehyde. This is the case if we had started with a primary alcohol. If this were a carbon in this second position here, then we would have formed a ketone. Now the interesting thing about aldehydes is that they can be subsequently oxidized and form a carboxylic acid. Because we're not looking at the mechanistic detail, I'm going to argue that in this case, our oxygen atom from our oxidizer comes and inserts an oxygen atom into that alpha hydrogen position. Notice that whenever oxidation occurs, the number of bonds between carbon and oxygen increases from an alcohol with 1 bond to a ketone or an aldehyde in this case with 2 bonds, and now to a carboxylic acid which has 3 bonds to oxygen. Carbon to oxygen to hydrogen is always the way that things bond. In order to be oxidized, a hydrocarbon must have an alpha hydrogen. The alpha hydrogen is a hydrogen that's attached to the carbon to which the functional group is also attached. In this case, we have a primary alcohol. We can oxidize primary alcohols because they have an alpha hydrogen. The product of oxidation for a primary alcohol is an aldehyde, which also has an alpha hydrogen. And so the product of oxidation for aldehydes are carboxylic acids. Returning to our alcohol now, this time with a secondary alcohol, we can see that we still have an alpha hydrogen, but we only have one of them. So when we oxidize to form a ketone, there are no further oxidation steps available to that species. And finally, a tertiary alcohol, which has a structure like this, with no alpha hydrogens, cannot be oxidized. There are mild oxidizers that we need to understand in our course. Those are a copper catalyst and limited acidified dichromate. Harsher oxidizers are when we have acidified permanganate or excess acidified dichromate. You can see here that we haven't limited the amount of dichromate to make this harsh oxidizer reaction. Mild oxidizers will react with a primary alcohol to produce an aldehyde. A harsh oxidizer will react with a primary alcohol to produce a carboxylic acid. Any oxidizer, either mild or harsh, will react with a secondary alcohol to produce a ketone. And as we've said, no oxidizers will react with a tertiary alcohol. Because they don't have an alpha hydrogen, they can't be oxidized. We're going to return now to our hydrocarbon flowchart, which you can see here. We've already talked about all of these reactions, and so it remains to add the reactions of our alcohols. Primary alcohols are going to react with mild oxidizers to form aldehydes. Aldehydes can be oxidized by any oxidizer to form a carboxylic acid. If instead of a mild oxidizer, our primary alcohol reacts with a harsh oxidizer, we skip the aldehyde and go straight to the carboxylic acid product. If we start with a secondary alcohol, any oxidizer will turn that into a ketone. And so we've revealed more of the hydrocarbon flowchart. As I said before, this is the same one that you'll have in the information sheet, which will be available to you both during tests and during the end of your exam. The last thing we need to do is look at the reactions of alcohols with reactive metals. Any species where a hydrogen is attached to an oxygen can react with alkali metals to remove the hydrogen. This is a redox reaction where the metal is oxidized and hydrogen is reduced. This is the exact same reaction that we get between water, which you can think of as a hydrogen attached to a hydroxide, reacting with sodium or potassium or lithium metal. We've seen those demonstrations and we know that they catch on fire. The reason they catch on fire is because lots of energy is released, heating up the hydrogen gas that is the product of reduction of that reaction. The hydrogen gas then ignites and you can see a flame. In our course though, we need to know that this reactivity is observed in all three types of alcohols, primary, secondary and tertiaries, and also carboxylic acids. Aldehydes, ketones, ethers, amines and amides don't react with alkali metals in this way. When alcohols react with alkalis, they produce alkoxides. When carboxylic acids react with alkalis, they produce alkanoids. We'll look at that in a separate presentation where we look at the reactivity of carboxylic acids. And so as I just hinted, we need to talk about the salt of an alcohol. Now here we have the general formula for an alcohol, which is an alkanol, because it's an alkane as an alcohol, so it's an alkanol. And that's going to form a metal alkanoxide as the product. Here's an example. If we add an alkali metal to an alcohol, we form our alkanoxide and hydrogen gas. I'll give you a chance to name both of these hydrocarbons. This is propan-1-ol. And our product is sodium propan-1 oxide. Don't forget the name of the cation first and include a space between them. And this final reaction allows us to update our hydrocarbon flowchart with one more reaction, sodium metal, to form the alkanoxide. That's it for today's lesson on the reactions of alcohols. I hope it all made sense, and I'll see you guys next time.